Hello everyone, welcome in this channel Mausam Science. Today we are going to learn an interesting topic of electromagnetism. Okay, motion of charged particle in a magnetic field. If a charged particle comes in a magnetic field, then what type of motion, what type of force does a charged particle experience? Okay, we are going to talk about that in this video. So before that, I have made a video on Lorentz force. Okay, you can check this video in upper I button or either in the description box. I want to justify this Lorentz force in a little bit. Okay, F is equal to Q E plus B cross B. It gives the force which will be experienced by a charged particle Q when it is kept in an electric field E or in a magnetic field B. So here we are talking about a magnetic field, then we can modify this formula as a F is equal to Q B cross B. Okay, that means what type of force will it experience if it is kept in a magnetic field B if the particle moves at the velocity V and the charged particle is of charge Q. Okay, this is the fact. Okay, this is the fact of this formula. Now we will notice that here is a cross symbol. Okay, and here is the small charged particle moving with the velocity v in this direction. Now what do you mean by the cross symbol? Cross symbol means magnetic lines of force. Okay, this north to south direction. If a magnet is there, okay, magnetic lines comes from north to south direction. If this magnetic lines is going from up to down like this in this direction, okay, if the magnetic lines go from up to down, then the symbol will be represented by this cross icon. Okay, I want to make clear, if the magnetic lines is going from up to down, okay, down through this paper, if it goes down by penetrating this copy, okay, by parsing this copy, okay, then what do we call that? Is called a direction represented by this cross. Okay, now if the charged particle is moving with the velocity v, it is going down, then what happen? It experience a force. But before that, let us consider, if it do not come move with the velocity v, then what happen? If the charged particle is still here without moving, then it do not experience any force. If the velocity is 0, this cross product is 0, then force experienced by the charged particle is 0. That means if the charged particle do not move, then it do not experience a force in a magnetic field. Okay, I hope the explanation is clear up to here. Now let us consider the charged particle is moving with the velocity v. Okay, if the charged particle is moving with the velocity v and the magnetic field is of value b, now, in which direction the charged particle experience a force? We need to find out with the help of this cross product. Let us forget about the charged particle, okay? Q, okay? There is one charged particle, it is moving in this direction. Now, the direction of the force experienced by this charged particle will be given by this formula B cross B. Okay? We need to know about the cross product A cross B, okay, is given by the vector C. So let us suppose. Then how to find out which direction will be C? If these two vectors are perpendicular with each other, then this direction of C will be find out. Okay, perpendicular means 90 degree. You can see here the magnetic lines B is going down and the other one velocity is going in this direction. That means these two are perpendicular, making 90 degree with each other. Okay, the angle formed between these two forces is 90 degree. So as a result, this value of vector C can be considered by the right hand thumb rule. Okay, if these two vector, any vector A or B, okay, if these two are perpendicular to each other, then the other perpendicular will be given by this value C. That means now we'll apply this concept in this diagram. Let us see the magnetic lines, anyone we can consider, okay, for the cross product. This will be our result, this two will be the given value. Let us consider now what happened is this finger is going down in the direction of magnetic field, okay, and this one, okay, this finger is going down and this one shows the direction of velocity. Okay, I hope the explanation is clear. If I do like this one is finger is down, this finger is in this direction of velocity. You can see here velocity is in this direction, the finger is shown by this one, and this thumb, okay, thumb is the direction of force experience. Now what to do? Now thumb shows the direction towards me, okay, thumb shows the direction towards me. You can do this, check it by yourself, okay. Thumb shows the direction towards me. So as a result, the force experience will be in the other side. Okay, this is the direction of force. Okay, magnetic field is downward direction, velocity is going this direction, and the force experience will be in the this direction. Now where does this charged particle go? Now you can see charged particle is moving in this direction, and due to this magnetic field it will be attracted in the other direction. So the charged particle takes the resultant direction, okay, in this direction. Charged particle tries to go in the other direction. So now the velocity direction will be changed. Charged particle direction will be changed. So as a result, from here, where does the charged particle go? Now again we can apply same rule, okay. Magnetic field is not disturbed, okay. We can apply the magnetic field downward, and charged particle direction, before the charged particle direction was straight. Now the charged particle direction is little bit moving. Now where does the thumb indicate? Now the thumb indicate, okay, you can see here as my this finger moves, okay, the direction of thumbs also moves, okay. So as a result, before the charged particle was here and thumb was showing in my direction, okay, in the direction towards me. Now charged particle moves, then the thumb also moves in the certain value, okay, it shows the direction towards me. Now what even if the charged particle takes this direction, then thumb shows the other direction, and the resultant will be in this direction. Now what happens? At every point, okay, now the charged particle tries to move in this direction. Again, due to this, if we apply the value, magnetic field down, this, okay, magnetic field is down, and this one is in this direction, then the thumb indicates in the other direction. So what happened? From here, okay, the charged particle will be attracted in this the other direction, and the resultant will be here. So as a result, I mean that the charged particle will be, before the charged particle was moving in this direction, it will be attracted to the other. Now if the charged particle is moving in this direction, it will be attracted to the other side. So as a result, the charged particle will take a circular motion, okay. Charged particle, it tends to move in this velocity before, but due to magnetic field, what happen, in every point the charged particle will be exerted a force, okay, by this magnetic field. The force is called a Lorentz force. So this Lorentz force gives the direction for charged particle, that is a circular direction. So from here we are clear that motion of charged particle in a magnetic field is a circular direction. Now let us talk about the other one, okay. If the magnetic field is in this direction and charged particle is moving perpendicular, okay, then what happens? I'm changing the direction of magnetic field now, okay. This is the direction of magnetic field, this is the direction of velocity of charged particle is moving in this direction. Now let us take this. Where will be the resultant force? It will be given by this thumb, okay. Now what happens? Any one finger can be shown with the direction of this one B, okay. This shows the magnetic field, this shows the velocity. Now where is the thumb? Okay, you can see the thumb is pointing downward, okay, inside the copy. So what happens? The charged particle will take the direction of circular motion throughout the copy, okay. It will take the circular motion throughout the copy by this way, okay. I hope it is clear. So if the magnetic field is inside in this case, then it is taking the motion in this copy like this. Now I am changing the direction of magnetic field in the other one, okay. Now the charged particle tends to move in a 3D diagram, okay, inside and out of the copy. Suppose this is the copy, okay, this is the paper, okay, this is one paper, then the magnetic lines will be like this, from down to up. Okay, this will be the circular motion in this case. Now again, in another one, I want to deal about the last case. Okay, this is the magnetic lines like before, and the velocity will be by making some angle. Okay, now what happened? Before it was straight, either if the magnetic lines was in this direction, the velocity will be either down or up. But here velocity is in with the certain angle to that down and up. Now what we'll do? We will take the two resultant of this one. If the force is acting in this direction, then we can take a two component, one component towards one perpendicular, another component towards the other perpendicular. Suppose the velocity is in this direction, magnetic field is in other direction. So what happened? Now it have two component. One component is in this direction. We know that if the charged particle move in this direction, then what happen? Now we will forget about this. We will take the two component. This velocity is acting in this direction means it have some velocity in this direction, it have some velocity in the other direction. Okay, like this. Because if it have a two direction, then it can go from the middle. Okay, as a resultant. So now here, if we are given the velocity before in this direction, then it have some component in this direction, it have some component in the other direction. So what even? Now this downward motion, okay, we can see here, if the velocity is in downward motion, it can make a circular motion in this copy. Okay, it can make a circular motion in this copy, through the copy, up and down. So now as a result, now what even this about this component? Can we forget this? No, because it is supporting for this velocity. If we used to talk only of downward, then the question was solved over here. It is making some angle with this component, so that means it have the other component too. So as a result, if the velocity is in this direction, what happen? Let us check it with this formula. F is equal to B cross B. Okay, we'll keep the value of Q as a constant, or let it be. Okay, we just deal about the direction right here. Okay, now what happen? The direction, the magnetic lines is in this direction, velocity is in the other direction. What is the angle between these two? Is 0 degree. If the value is 0 degree, okay, then BB sine theta will be 0 degree, then the force experience will be 0, because sine 0 degree is 0. That means if the velocity component have the other direction, then the force experience will be 0. That means the particle can straightly move, okay, in the other direction. We have two cases. At what case the Lorentz force will be 0? If the particle do not have any velocity, if the particle moves with the velocity parallel to the magnetic field, that in that case, in that two case, okay, up to here we have discovered that the Lorentz force will be 0. Okay, if you have any other ideas, you can leave that in a comment section, let me know. Okay, something from your side too. Okay, this too. Now as a result, now what happened? The particle can move in this direction too, and it can move in the direction of circular field. Then what happened? It can create a helical motion. It is slowly going in the forward direction. Okay, or what we call this backward or forward. Okay, it can go in this direction too, and it can make a circular motion. So the video is too lengthy. Okay, it is a 14 minute. So today we have learned about the motion of charged particle in a magnetic field. We have dealt about the different cases. Okay, it is not a big deal too. Okay, conceptual. Okay, it is a conceptual part. Hope you know. If you know this video, okay, if you find this video interesting, hit a like button. Okay, share, and you can join my channel. Okay, share this video and leave some queries in the comment section. We'll meet again. Bye bye.